Welcome to the walkthrough for Assignment 1, Part B. The objectives of Part B of this assignment are to learn how to synchronize Java threads via a semaphore and a spin lock. Videos describing Java semaphores appear on my YouTube page. There's also a video describing spin locks there as well. I recommend you watch all these videos to ensure you have a basic understanding of these Java synchronizers. Of course, we'll also cover these topics in class as well. In this part of the assignment, you'll use a semaphore and a spin lock to enhance the multi-threaded implementation of the Palantiri Simulator app that you began in Assignment 1A. Assignment 1B focuses on the Palantiri Manager, which is an object that's used to restrict the number of beings from Middle-earth who can concurrently gaze into a fixed number of Palantiri. If you're not yet a fan of Tolkien's Lord of the Rings trilogy, you should drop everything you're doing and read about Palantiris here. The Palantiri Simulator app is packaged as a project in Android Studio version 3.x. The app itself is written in both Kotlin and Java and demonstrates many Android capabilities. For the purpose of Assignment 1B, however, you'll only need to be aware of the following three directories. The first is the manager's Palantiri spin lock hash map, which contains the skeletons you need to fill in, as we talk about in just a minute. There's also an app source test directory, which contains a set of JUnit tests that exercise many Palantiri Simulator features and can be used to help test the functionality you implement for this assignment to make sure it's correct. Finally, there's app source Android test, which is an Android Studio instrumentation test that can be used to run your app automatically. As before, you'll need to open the provided Android Studio project, and once it's open and synced properly, you can run the project by clicking the green Run App button in the Android Studio IDE, which will automatically prompt you for an Android emulator to run, assuming you've already created one and installed it. Once again, if you have any problems with this, please come to office hours and we'll help you get the Android emulator running. I'll also show you shortly how to run the various types of tests as well. There's a number of to-do tasks that you'll have to implement in order to complete Assignment 1B. Once again, please do not change the overall structure of the skeleton, just fill in the to-do task. In particular, you need to finish implementing the to-do task for this assignment in the spinlock hash map folder. The two files you'll focus on are called spinlock hashmapmanager.java for one, and you'll need to complete the to-do tasks in various methods and in the class itself in order to implement the Palantiri Manager via a semaphore, a type of spinlock, and a hash map. The second file you'll have to implement depends on whether you're a grad student or an undergrad. Undergraduates need to implement spinlock.java by completing the various to-do tasks in methods and in the class itself in order to emulate a compare and swap style spinlock with so-called non-recursive semantics. In contrast, students taking the class for graduate credit have to implement something called the Reentrant spinlock.java class, which I'll talk about in just a moment. After you finish those implementations, you go ahead and run your program, and again, it's considered correct if all the beings successfully complete all their n iterations. So a correct simulation should restrict the number of gazing beings to the number of Palantiri, so that if there's only 4 Palantiri configured in the simulation, then only 4 beings should ever be gazing at the screen at any given time. While the simulation runs, you'll be able to get visual feedback showing the states of the Palantiri and the beings, as well as the progress of the gazing that's taking place. If your implementation is correct and doesn't throw any exceptions, the title bar labels will appear as green when the simulation completes. However, if your implementation throws an exception or has problems with the implementation internally, when the simulation completes, the title bar labels will be displayed as red. Moreover, you should run the tests in order to be able to make sure that your implementation passes the unit and instrumentation tests. Graduate students have some additional tasks they have to take into account, or students who are taking the class for graduate credit have to take certain tasks into account. In particular, they need to implement the spinlock hashmapmanager.java file to replace the spinlock class with an implementation of the Reentrant spinlock.java class, which emulates a compare and swap style spinlock with so-called recursive semantics. We'll talk about that shortly. Undergrads are welcome to implement these features and methods, but it's not required. The skeleton code for this assignment can be downloaded from my GitHub account. Assuming that you've already set up your GitLab account, you can simply go ahead and pull the skeleton code into your repository, reading it carefully in the directories we've described, and completing the various to-do task markers. The additional work that the grad students need to do is clearly marked. This assignment is designed to help you get familiar with writing multi-threaded programs using the Android Studio IDE and core Java synchronization mechanisms. It is designed to complement the Java multi-threading mechanisms that we used in Assignment 1A. This assignment, however, doesn't require you to program any Android concurrency or communication frameworks, which we'll cover in upcoming assignments. Now that I've given you an overview of the assignment, let's drill down on the various skeletons you'll need to implement. These skeletons all reside in the Managers, Palantiri, Spinlock Hash Map folder. We'll start with the Spinlock Hash Map Manager class, which everyone needs to implement. This class extends the Palantir Manager and uses a spinlock, a semaphore, and a hash map in order to be able to restrict access by many being threads to a fixed number of Palantiri. You'll have to provide a field that is used to implement the spinlock. This spinlock, in turn, will be used to ensure that threads serialize on the critical sections we'll look at below. There's two different spinlock implementations. One, which is the spinlock class, which undergrads have to implement, and the other is the Reentrant spinlock class, which students taking the class for grad credit have to implement. In either event, you need to define an instance of that here as a field. You'll also have to define a counting semaphore that limits the concurrent access to the fixed number of available Palantiri that are managed by the Palantir Manager. I provided you an implementation of a Palantiri map, which is a hash map that associates the Palantiri key to a Boolean value that's used to keep track of whether the key is available. You'll see how that gets used in just a moment. There's a hook method called back called build model that's called by the framework. And this is used to initialize the various fields we just described. So we go ahead and make a new hash map. And then you'll have to call the getPalantiri factor method and use the result that comes back to that in order to be able to initialize the Palantiri map with the appropriate values. You'll also have to initialize the semaphore to use a fair implementation in order to mediate concurrent access to the given Palantiri. And finally, you'll have to implement the spinlock field. So those are fairly straightforward things to do, but you have to think through how to implement a fair semaphore. That's probably the thing that'll take little doing. Down here is the acquire method. This method is called back in order to be able to acquire a Palantir, and it's intended to block until one is available if there isn't one available right away. So the way this works under the hood is you'll use the semaphore in order to uninterruptibly acquire a Palantir, or rather, let me rephrase that, in order to wait until there's a Palantir available. And then you'll use the spinlock in order to ensure that only one thread at a time can actually come in and check the hash map to find the first key whose value is true. And this, of course, has to be done with the lock held so that you don't end up having race conditions when concurrent threads would update and access the hash map simultaneously. Once you found a free Palantir in the hash map, then you need to set its value to false to indicate that it is not available. And then that Palantir will be returned to the client and you'll release the spinlock. All the code I just described needs to go here. There's also a little check, sort of a sanity check at the bottom of this method that will throw an illegal state exception if something went wrong. So make sure that you return properly, and if things go awry, make sure you go down here to throw this illegal state exception. Here's the release method. The release method is, of course, the inverse of acquire. It's intended to return the Palantir back to the Palantir Manager, so it's available for other beings to use. And the way this works is the Palantir is passed back in. You'll need to be able to use the spinlock in order to make sure you have exclusive access to the hash map. Go ahead and change the value in the hash map, set it to true, saying it's now available for reuse. And then you'll release the spin lock. And then you'll also go ahead and increment the semaphore to indicate that there's now a possibility for another thread to go ahead and get access into the Palantiri manager if there was a contention for the number of beings that were currently gazing with the limited number of Palantiri. So those are the methods that you have to go ahead and implement. Here's a little hint. I call the field M available Palantiri. That's just the name that I used. Up here, when I defined this, you could call it something different if you wanted to, but that was what I happened to call it. So probably wouldn't be a bad idea to use the same name. It's currently colored in red because I have taken that definition out, so you'll have the fun of figuring out how to do the implementation yourself. Let's go take a look at the skeleton for spin lock. This is what the undergraduates have to implement. So the spin lock is used to emulate a compare and swap style spin lock with so-called non-recursive semantics. That means that once a thread acquires a lock, it cannot reacquire the lock unless it releases it first. The way you're going to do this is you're going to use something called an atomic Boolean, and that has a method called compare and set. And the default state of the spin lock should be unlocked. So you'll have to go ahead and define an atomic Boolean with those properties set here. There's a method called try lock, which is used to do a non-blocking acquire. So you'll have to go ahead and use the atomic Booleans compare and set method correctly here to do that check. The main method that you'll use is the one that's called lock. This is the one you have to implement. This is used to check to see whether or not the whether the lock is available. And if it's unlocked, then we're going to atomically lock it and then return. If it's already locked, we're going to continually spin, waiting for another thread to release that lock. So that's where you're going to have to use the atomic Boolean compare and set operation in order to do that. And there's a method, there's a field rather called mOwner, which is what I called the atomic Boolean. So I called it mOwner for lock owner. And this describes how you'll need to do this. You'll need to have a loop here that keeps trying to atomically set the value to true. And you should also, each time you try and fail, you should also check to see if a shutdown has been requested. And if it has been requested, then you want to go ahead and throw a cancellation exception. So you're going to check to see whether cancellation has been requested, and if so, it'll shut it down. Unlock will simply atomically set the Boolean to be false. In other words, it's now available for use. So you'll have to do an atomic operation. Of course, everything on the atomic Boolean is atomic, but you'll have to call the appropriate method to set the value of the lock to be false, which means it will be released. So we'll talk about how spin locks work in class, but these are basically the things you'll have to implement in order to make this work properly. Let's take a look at what the grad students have to do. The grad students have to implement a spin lock that has so-called recursive semantics, which we call reentrant. So a reentrant spin lock is like a spin lock, but it has this reentrant property. And all that means is that if a thread currently owns the lock, then it can reacquire the lock, simply incrementing a recursion count without having to release it first. So it makes it recursive. So basically, what you're going to have to do here is define an atomic reference that's used as the basis for the atomic compare and swap. And the default state of the spin lock, of course, should be unlocked. Now, the way you're going to do this is we're going to actually keep track of the thread ID that's the current owner of the lock. And so you'll have an atomic reference that's parameterized by thread. You'll also have to define a field that will count the number of times the owner thread has recursively acquired the lock. And so it just has to be a simple count, nothing fancy here. You can use an int, for example, as long as you give it the right default value. Over here, you have to implement the try lock method. This is the one that's used for non-blocking acquisition of the lock. And what you'll have to do there is fill in the value to basically try to set the owner's value, which this is the owner of the reference, to the value of the thread, which is considered true. And this will succeed if and only if the current value is null, which indicates false. So that's just sort of a one-liner. Down here is really the workhorse method. This is the lock method. Similar to the one that the undergrads have to implement, the main difference here is that you'll have to get the current thread, and then you'll use the thread reference in order to be able to try to set the value of the atomic reference to the current thread reference. And that thread reference, of course, will be non-null. And so you'll have to keep checking to see whether or not you can atomically do compare and set to set the value of the atomic reference to the thread reference, and then check to see whether it's null. So you'll have to figure out how to do that. Once again, you'll have to check each time you fail to do the set atomically, when you fail to get the exclusive access, to check to see if you've been canceled or not. And then if you haven't canceled, you have to throw a cancellation exception. Unlock simply goes ahead and sets the value back to null, the value of M owner, which is the atomic reference, back to null, but only if the recursion count is going to be equal to 0. If the recursion count is greater than 0 and the calling thread, the thread that calls on lock, is the one that currently owns the lock, then simply the recursion count is decremented by 1. So only when the count is 0 and the calling thread is the thread that owns the lock will we atomically release the lock that's currently held by the owner. So those are the various classes you'll have to implement in order to be able to do this part of the assignment. The key thing you'll be learning here again are semaphores in order to be able to mediate access to shared resources concurrently, as well as spin locks, which are used to guard critical sections from simultaneous access in order to be able to prevent race conditions. Now that we've walked through the specification for assignment 1B, let me go ahead and run the tests to show you what should happen if you've written your code correctly. First and foremost, make sure you run the tests. If you don't run the tests, it's highly unlikely that your code will work properly. And it's also very easy to tell what's going wrong if you do run the tests. Let's go over here and run the tests. You can see we'll go ahead and run the tests that are in the Vandy simulator folder. It's taking a second to compile and set everything up. And if you also take a look at the left-hand side, you'll see that we're running tests not only for 1B, but also we're rerunning the tests for 1A. So this way you can make sure that any changes you make to your code don't break the 1A tests. If you take a careful look, you can see that all the tests that were run here have green check marks by them, meaning that they successfully completed. And there's also some information that's printed out here, which you're welcome to take a look at, although it's more for helping us know what's going wrong in case you have some errors with your code. So again, make sure you run the tests. Everything should be green. If you don't see something that's green, make sure you take a look, try to fix it, and feel free to come by office hours or post to Piazza if you have any questions about this. Now that we've run the unit tests, it's time to show you how to run the instrumentation tests. We'll click down here and go ahead and say, run the instrumentation tests. As you can see, everything starts up, things are being loaded. And over here, we can see the Android emulator. Let's go ahead and do a couple things. Let me show you the Android emulator here. It should start running. As you can see, it's basically doing a torture test of your application, rotating the screen, having many different beings gaze on a smaller number of palantiri. In this case, we have 10 beings that are gazing at 6 palantiri for 10 iterations each. You can see it keeps track of the number of iterations. If it works successfully, everything should be green. If for some reason you have some kind of a bug in your code, then you'll see red show up there. And this will keep running on and on. If you take a look over here and go to logcat, you can actually see what's happening as things are running. We'll have to wait till it starts running again. There we go. It's tearing it down, bringing it back up again. Going to go ahead and do some more torture tests here momentarily. Unit tests are really good to exercise and evaluate the performance of individual components. But of course, what really matters when all is said and done is how the app works. So you can see here that this is printing information out as things are running. If something goes wrong and your program crashes, I recommend you take a look at logcat. It will most likely tell you what is going wrong with your code. Going back over here, you can see that this thing keeps doing the torture test over and over again. And it's just a really nice, easy way to get a feeling for whether or not your app is working properly or not. So I strongly recommend that you use the instrumentation tests in order to be able to evaluate whether your app is actually running. This will keep running for a while. Of course, it's all going to work properly because I wrote the code correctly, but you should get in the habit of running these tests, taking a look at the output from Logcat, and making sure that everything is green when it actually performs.